Claire, can you hear me?
Yes.
Nice. Did you hear a large echo? A little bit.
Yeah, at first when you unmuted, it was actually I'm hearing myself while I'm talking. Yeah, there is an echo.
Yeah, hold on. What about now? Is it better?
Yeah, sounds a lot better.
Okay. Yeah, I guess you are the you are the only one right now. Should we stay here for like another minute to wait for other people join? Or probably not.
Either way, it's fine by me.
Just a second.
The audio was bad just then. It was like a ringing sound.
Okay. Okay. So, all right. I guess I started recording, and all right. So today we are going to go over the um, problem set number 2, right? So let me share the screen with you. Uh, there you go. So problem set number 2. Most of the student has already submitted. So uh, a lot of the mathematic calculations required in this problem set, but I will walk you through uh, for today. And if you have any question, please just jump in and let me know anytime. Well, I guess there's only one student, Claire, so you could just kind of like a discussion with me. Like you don't have to worry about anything. Just speak up, and then we could try to sort things out. Okay, so let's take a look at the first question. So first problem asks you to describe the stationary restriction for the AR1 process. So we know AR represent as autoregressive, right? Autoregressive process. And AR1, if we're using mathematical representation, it looks like this. So suppose that YT is time series process, or it's a time series random variable. Yt is equal to alpha naught. Or alpha naught is a parameter, and alpha 1 times yt minus 1 means what? Means this period's the current period's stochastic outcome depends on the last period's outcome and a shock. Okay, and we know that the shock follow a white noise process. So white noise means what? White noise means epsilon t is follow a normal distribution, and its expectation is equal to 0, and the variance is equal to like one of the parameter. Right? So the first question is define and explain in your own words, okay, and formally in parentheses a definition of the stationarity. You are required to provide a specific citation to a lecture notes or test will use the answer to this question. All right, so I will just go over the basic definition of the stationarity, weak stationarity, and the strict stationarity. The second part is derive and describe the necessary and sufficient condition for AR1 process to be stationary. Okay, so let's do it. So we know that right now our our process look like this. So it looks like YT it's equal to alpha naught plus alpha 1 yt minus 1 plus shock. Right, so this is the current period outcome, right? And this one is the that one period outcome, and this is the current period shock. Right, in plain English, it's like this. Okay, and obviously yt is a random variable. It's follow AR1. Okay, and AR1's representation in math is like this. Epsilon p is like white noise, and white noise means it's a normal distribution. Expectation is equal to 0, and there is a parameter for their variance. Okay, so first of all, how do we define strict stationarity and weak stationarity? So mathematically speaking, strict means we need more conditions to satisfy, right? So all the moments of the time series process has to be time independent, right? So this is the typical definition of the strict stationarity of a process. Okay, what about a weak one? So the weak one is the first two moments, right? So the first two moments. Oops. Did I lose my connection? No. The first two moments of the time series process have to be time independent. And if you take a look of the chapter number 2 in Anders, you might be able to find out the definition. Okay, so that is your own words. And for the formally definition, it will be looks like like this. Formal definition. It will be looks like expectation of the time series variable got to be mu for all t, right? So this reverse a notation means for all in mathematically. Okay, for all t. And what else? The variance of this got to be some parameter which is time independent as well. So as you could see here, no matter is the u or the sigma square y, there's no subscript t. So that means this u will be a constant across the time, and this sigma y square will be constant across the time. And the second moment of the time series process, not only the variance itself, right? So we need to check the covariance. Right? So there's another one. So covariance, for example, yt minus 1. This is we call gamma 1. In our notation, right? So this is the leg 1 period's covariance, and covariance YT, YT, that's 2, gamma 2. All the covariance has to be time independent as well. YT has to be time independent as well. So that basically is the idea of this question, right? So you have to specify out your own words, and you have to show me what kind of the definitions you have here. Okay. So for the covariance part, you could write like this. For the covariance part, you could actually write like this. So we all know that weak stationarity means what? This constant for OT. This gonna be a parameter for OT, and this gonna be just apply the definition of the covariance, gonna be gamma tau. So remember that this is a function of the tau. This is not a function of the t. So that means what? If I have random variables looks like this, and say that this is my y0, this is my y1, this is my y2, this is my y3, this is my y4, this is my y5. So if I pin down the lag period between them, say that I'm going to find out gamma 1. Gamma 1 means the covariance between these two variables, right? So y0, y1, y1, y2, y2, y3, y3, y4, y4, y5. They supposed to be the same. Okay, so this is important. Then that means if I pin down, so another example, that means if I pin down the tau is equal to 2, I try to find the covariance between two periods separate. Right? So those are called gamma 2, gamma 2, gamma 2, gamma 2. So if this is a weak stationary process, that means their covariance of the time series must be time independent, right? So the only things that we care is the leg, how many leg periods that you count. Okay, so let's move to the second question. We need to consider the necessary and the sufficient condition of the AR1 process. Can I erase now?
Yes.
Okay, thank you. Yep. So there are a bunch of ways to do so. Okay, so in order to find this, okay, so this is my mathematical representation of AR1. Right? So sometimes you will see the AR1 does not include this. So this we call drift or constants in our process. Okay, you will see it later on. So sometimes when you Google the internet, you will find this is like the normal AR1 representation. It's the same. This just give you like a shift of your own process. Okay, never mind. And how do we show that the process what's their necessary condition? So it should relate it to this parameter. Okay, so let's see how could we prove it. So this is my original condition. the best way, like the most intuitive way uh, to derive the general representation of this function is to use the iterative method, right? So yt, since yt is equal to this, seems like I copied down a lot from it. What about yt minus 1? Right? So now we try to replace yt minus 1 by the yt minus 2 and epsilon t minus 1. And this, intuitively, we could see looks like this. Okay? And now the next step is to plug equation 2 to equation 1. Right? And then yt, if we use the representation of the yt minus 2 and t minus 1, this will become my representation. Okay, and what's the next step? The next step is just to find the last uh, random variable, again, using the oops. Sorry, I just have a disconnection to my iPad. Oh, okay. Okay. Um, so yt minus 2, it's equal to alpha naught plus alpha 1, yt minus 3 plus epsilon t minus 2. Again, and then plug into this. This is equation 3, plug into equation 2 plug, and I will get yt, it's equal to alpha naught plus alpha naught alpha 1 plus alpha 1 squared, alpha naught plus alpha 1 yt minus 3 plus epsilon 2. Right? So if you do a little bit of the organization, you organize your iterative function. This is the general representation. This is the general representation, okay, of this AR1 process. Supposed to be I plus t naught I equal to 0, t minus 1, alpha 1, I, t minus I. So there are two components here. One is the shock that happened before, and is the one is the coefficient that related to the previous period, right? So let's see if I have this. What's the next step for me to uh, find out the expectation? Can I erase right now?
Yeah.
Okay. Yeah, just let me know anytime. Moderator. Okay, so now I can erase it. So, like I said, we have this as our general representation. right? And if we take the expectation, what will we get? We will get an expectation operator outside of the right-hand side equation, right? So from the last week, we know that if I have a random variable that looks like this, I could factor out the non-random part, right? So what will we get? We will get E yt, it's actually equal to alpha naught plus, right? So this is the only random part here. Okay, so expectation value will only come in here. The rest of them are the parameter. And because they are linear combinations, so you could factor out all the variables in front of them. Right, so next step is what? EYT actually it's equal to alpha, not this. This part is gone because epsilon follow white noise. Right? So now the thing is here. Okay? So if we have t is very large, t approach to infinity, EYT supposed to looks like what? Looks like a geometric matrix with the common ratio. It's equal to alpha 1. Right? And initial value is alpha naught. So this sum is equal to alpha naught over 1 minus alpha 1 if alpha 1's absolute value is smaller than 1. Right? So this is the mathematics rules or like the backgrounds that you need to know. But if we apply this, here comes the necessary and sufficient condition for the time series process of yt becomes stationary. It's here. And that basically is it. So we need to find out second moment as well, right? So second moment, and using the same idea of this to find out the necessary and sufficient condition. Okay, so this is the most intuitive way to find out the first moment, but actually there are some of the easiest way to do so. So if we go back to the mathematical representation of this process again, what are the easiest way for us to derive it? Yt is equal to alpha naught plus alpha 1 y minus 1 I minus t minus 1 to follow this. Okay, so if we just simply take yt, take the expectation operator in both hand side of the equation, this is what we get. And we know that yt are going to be looks like this. And the last part, as we know, this will become 0. So EYT will become alpha plus alpha 1, EYT minus 1. Okay, so now if YT is AR1. That means YT minus 1. Their expectation supposed to be the same. Okay, by using this rule, EYT 1 minus alpha 1 equal to alpha naught. EYT could be alpha naught divided by 1 minus alpha 1. So this is consistent with the iterative method, right? And all we need to make sure is that this have to satisfy one of the important conditions is that alpha 1's absolute value have to smaller than 1, right? So you have to make sure that this part is smaller than 1, okay? And this move forward to the future classes. This is actually called unit root condition. Okay, so if your process is satisfy the unit root condition, your process will be stationary. That is the whole idea here. Okay, and now we need to find out the second moment of this process as well. So let's take a look of the second moment. So once again, it's the same thing. We need to start it from the origin representation. Okay, and this time we use variance. Right, so what's variance T now we have? The next one, the first, it's not random, right? So non-random, we could just get rid of this. And now I have a coefficient in front of my random variable. So once again, using the rules of the variance operator, this is what I get. Plus the last term's variance, right? And what about this term and this term? So we know that AR1 is actually a stationary process, right? So VAR YT supposed to equal to VAR YT minus 1. So using this trick, we can have and variance epsilon, it's actually equal to sigma squared, right? So variance YT that we found out is this. So this will be variance YT for AR1 process. So sometimes we use another term to describe this. Gamma 0. What's this? Covariance of same period outcome. Right? Now, we need to figure out what else. The other covariance, right? The variance between YT and YT minus 1, and the variance between YT and YT minus 2. Okay, so let's do it. Covariance YT minus 1. Okay, by its definition, something like this, right? Okay, and now we need to find I need to find no, hold on. So covariance yt minus 1. Why don't we just using covariance function? That'll be easier. Covariance yt minus 1. Covariance alpha naught alpha 1 yt minus 1 plus epsilon t alpha naught plus alpha 1 yt minus 2 plus epsilon t minus 1. Okay, and then let's see. Using, so this one we could get rid of because it's not random. So now it's covariance so okay, so the first term covariance uh, second term, right? And then third term, last term. Okay, and what you get? You will get alpha 1 squared covariance yt minus 1 yt minus 2 plus, what's this? This are going to be variance, just the variance of epsilon 1, right? Because yt are going to be squared. Yt are going to be alpha naught plus alpha 1 yt minus 2 plus epsilon minus 1. Right, so no, this is just alpha. And this two terms, this becomes 0, and this one becomes 0 as well, because yt minus 2 does not relate it to epsilon t, right? So now I have everything I need. So gamma 1, it's also called covariance leg 1 period, right? So gamma 1, it's actually equal to this gamma 1 plus epsilon alpha 1 epsilon. So 1 minus alpha 1 squared gamma 1 is equal to alpha 1 epsilon. So what are the gamma 1? What are the covariance between yt and yt minus 1? That will equal to 1 minus alpha squared alpha 1 squared. Okay, so this will be my answer for the Ar1 process. So let's move on to the second question. MA model. Okay, moving average model. So consider a following model. Okay, let me share my screen with you. Okay, let me show. Well, so one more thing for the AR2, if AR1, the second, you could still apply the same techniques, and you will find out that actually uh, after like when you expand it out, you will find out the correlation between yt and yt minus 2 are equal to 0. So that will be the AR2's uh, AR1's that period 2 covariance. Okay, so let's move to problem number 2. If now I'm looking at a moving average model instead of the AR1 model. So this is what MA1 looks like. So should I go over the file? So, okay, zoom in a little bit. Okay, now consider the following MA1 model. MA1 model looks like this. So instead of being like YT is being affected directly by the last period's YT minus 1, now YT actually was a weighted average between this period's shock and the last period's shock. So this is a very like salient fact for the moving average model. So if you ever see like a process, its composition, it's all rely on the previous and the current shock. This one's supposed to be the moving average. Okay, so MA2, as you could see, supposedly this looks like what? MA2 will be like two coefficient here. Instead only have one. MA2 will be like epsilon and like 2. So once again, we need to find out the stationary, whether this one is a stationary or not. So stationary is sufficient and necessary condition. Again, we check the first and the second moment and the covariance between the different period of the random variable. That's it. So let's take a look of how do we do so. Let me go back to the blackboard, whiteboard actually. So YT it's equal to epsilon p plus theta, this. And we know that epsilon follow white noise, that means normal. And the variances, it's sigma squared. Okay, so is YT stationary? So is it weak stationary? So let's check. Exploitation operator put on the right hand side and left hand side simultaneously, and then use a law of the distribution that I will get this and this. Right, so follow the information I know. This is equal to 0, this is equal to 0. So EYT equal to what? EYT equal to 0. And 0, it's a parameter. It's another random variable. Does not depend on t. So this EYT is time independent. Right? Okay. And the next one, what about variance YT? Variance YT is equal to variance, okay, this plus this. Okay, so I have two random variable in my parentheses now. Variance xt plus yt is equal to variance xt plus 2 covariance xt and yt plus variance yt, right? So using this rules, variance this plus variance this plus 2 covariance this and this. What will we get? We will get this is epsilon t. This is, well, remember it's squared here. Epsilon t plus 0. Okay, and this will become 1 plus epsilon t. Was this time independent? The answer is yes. right? So the first two central moment we already figured out. Okay, now I need to figure out the next one. That's the harder one. That is what? That is the covariance between yt and yt minus 1. So how do I figure out this? So the easiest way, give me a second. Okay, so easiest way would be using the covariance definition, right? So covariance yt minus 1 is actually equal to expectation of yt minus mu yt minus 1 minus mu, right? And now if I found out this, I would have or we can use this. We can use this formula. This will be easier. So if I use another form of the covariance formula, looks like this. This is what I get. Right? The combination, the second moment of this two random variable, the product of those two random oh sorry, I need to zoom back. The product of those two variable minus their first moment's product. Okay, and we know that what's this? This will equal to 0, and this will equal to 0, given they are the moving average process. So covariance yt minus 1 actually is equal to expectations yt minus 1. So now things will become easy, right? So just plug in. So expectation yt, that's equal to epsilon t plus psi t plus 1, epsilon t, sorry, this is minus 1 plus this is 2. And then using the rules of the distribution, right? So this will become so as we could see in the next step, okay, the next step is like this, put the expectation operator inside of the parentheses. Okay, so let's see, what is this term? This term are gonna to be equal to 0. Why? Covariance of the ET minus 1 is equal to 0, right? And this term is actually equal to this. And we know that the central first moment of this white noise are equal to 0. So covariance this actually equal to this one. This will equal to 0. So same thing, not in the same period will equal to 0. This will equal to 0. This will remain as sigma squared. This will become 0. Okay, so covariance yt minus 1, it's actually equal to this for Ma1 process. Okay, so let's see. What about the covariance 2 lag period? So now I want to know what about this. Okay, so same idea. Covariance yt minus 2 is equal to expectation yt minus 2 minus yt minus 2. Right, and because this is a moving average process, I know this is equal to 0, this is equal to 0. So all I care about is this part. Again, expectation yt minus 2, that's equal to expectation psi, what's the notation? Oh no, b t plus times what? Times epsilon t minus 2 plus t minus 3. So as you can see, this term is not correlated. This term and this term is not correlated, or covariance is not. This term is not. This term is not. So this is equal to 0. So covariance yt minus 2 is equal to 0. So what do you have right now? Gamma 1 for the MA process, covariance yt minus 1, it's equal to 1 minus theta. This gamma 2 covariance yt minus 2, it's equal to 0. So what is the correlation? So low 1 is gamma 1 divided by gamma naught, right? So gamma naught is actually just the variance of the yt. So this will equal to 1 minus divided by variance is what? Variance is something. So variance is one term. So variance is just one term. So this one will be larger than 0. And gamma and low 2 will be gamma 2 divided by gamma 1. So 0. So if you take a look at the cologram, this will be looks like T 1, 2. Ma1 will looks like this. Cologram. This is one of the value and one of the value at second. Something like this. Okay. Well, so actually, the number it's like this. The values looks like this. For Ma1 process, gamma naught is covariance YY, right? It's variance Y. It's looks like this. Gamma 1 covariance yt minus 1 looks like this. Gamma 2 yt minus 2 is equal to 0. So low 1 will equal to y, low 2 will equal to, right? So this will equal to 0, and this one will equal to something like this. Okay? So that will be it. And that will be for the second question. The third one is the R1. So I will post the code online. So but why not we just take a look of this question. So the number 3, question number 3. Question number 3 asks you to simulate ARP and MAP process of your preference. So you have to construct the autoregressive model with the order of the P, and MA, like moving average model, with the order of the P, like any kind of a model. So basically what you need to do is to tell R to simulate a process like this. And you could arbitrarily choose alpha naught and alpha 1. And for MAP, you could just choose the coefficient here and here, right? So the coefficient here and here, and here and here, and you can choose the order. All right. So let's take a look of what the answer key tell us to do. So first of all, you need to we need to tell R to, hold on. We need to give R a seed. So random variable, if we want to create a random variable, we need to tell, hold on, let me share my screen. So we need to tell R like what kind of a seed we are looking at. So here is what we need to do, is to type set seed, copy and paste from the, okay. So this one, if you run it, you will get like R will go over it. Okay. So this is telling you what are the random variable seed that we are using. So it's better for us to track your result is correct or not. And then we can just construct the model, and we could use the arima.sim. This function looks like this. So this means I assign the value of this variable, right? And this is, I tell R, the second part of this is I tell R to simulate an AR model, the alpha 1 coefficient is equal to 0.9. Okay, so this will give me a series look like this. So if I assign this one into a object, I could have ar1.sim looks like this. Okay, so n is equal to 1,000 means I'm choosing, I let R to run 1,000 observation. Okay, and then you could just plot, right? So how do you plot the AR1 in R? So basically you need to use ts.plot, right? So just run this code. And this is what I will get. AR1 sim ts plot. There's one packages I need to this. Okay, so this is what you see, right? So now, okay, so this is the function of yt equal to 0.9 times yt minus 1 plus epsilon t. Okay, and that basically is the first one question. So how do you figure out the ACF? It's relatively easy. So ACF for the Ar1 model is like ACF. Basically, you just type ACF, ACF, and your variable's name. Now you will see the autocorrelation function. And if the partial autocorrelation function is just using the PACF function in R, so it will be like this. So you will have partial ACF and ACF. So what are the salient factor right now we see from AR? So you see from ACF, okay, so let's go back to the previous graph. SEF, the AR1 decrease, right, each by each. And that is intuitive. Why? Because the AR1 model, AR1 process, it highly depends on the previous uh, outcome, right? So the autocorrelated function will not decrease suddenly. Whereas the PACF here, as you can see for the AR1 model, once the first period goes down, the PACF function becomes very, very small. So if we see a PACF looks like this, the first period spike, and then the rest of the period become within the small, like small interval confidence intervals of the zero, then this will be a function of the AR. So if you are going to make the deduction of this, what about AR2? So AR2 model will look like what? AR2 model will look like, if I go back to, for the ACF, AR2 model will be more smoother. Can I, can I draw on this? Can I? So the AR2 model will be like the the decrease will become smaller because it's not only depends on one lag period, it depends on two lag period, right? So autocorrelation function will become like this. The curve will become smoother. And the PACF of the AR model will become one spike here and another spike maybe downward here. Depends on your coefficient. If your coefficient is positive, then your spike 1 and your spike 2, and then since the three period, the PACF will within the confidence interval of the 0. Okay, so this is the part of the AR1 model if we're using R to simulate. What about the Ma1 model? So Ma1 model is pretty similar. So we need to create the Ma1 series, right? So first of all, we need to set a random seed. So we tell R what kind of the random variable you pick from. And now simulation looks like this. So now I make the coefficient of the Ma1. Remember the C is equal to 0.1. It looks like this. So this is my code to simulate 100 observation of the Ma1 model. So if I type this, you will see like 1,000 observation here. And this, if we assign it, give a name of the Ma1 simulation, it looks like this. And now I have another series called ma1.sim. So it's the same. I need to plot it out of the Ps plot, right? So plot it out. What should I do? I should just using a Ps plot, right? And okay, this should be okay. No. So This is my Ma1. So as you can see, this is very stationary as well. So excitation looks the same, and variation looks pretty time independent. Okay. What about ACF? Okay, so let's take a look of the ACF Ma1.sim. Okay, so as you can see, this is the factor. This is very important, unique factor of the Ma1 series. So, so remember that AR series, we take a look of the partial autocorrelated function. MA, we take a look of the autocorrelated function, right? So you see the first one spike here, the second one become very small, and the result in within a zero confidence interval, right? So this will give you the idea of this series is the moving average model. Okay, what about the PSCF? A1. Sim. PACF look like this, okay? So nothing really stands out here. So remember that once again, for the AR, take a look of the partial autocorrelated function graph. And for the MA, take a look of the ACF graph. So think about that. If MA2 process what the ACF looks like, the ACF will looks like the first spike here, the second spike, maybe it's close to the first one, and the rest of the correlation become very, very small, right? So that's the idea of the MA and the AR. Okay, so you just briefly tell me that you just briefly tell me the idea of the ACF and the PACF, and then tell me like what you see. You will get a full credit. Okay, so let's move on to the last question of this problem set. Sharing application. Okay, so a time series xt follows Ma1 process if this satisfies this. Okay, so it tells you a series looks like this. Okay, so now instead of being a AR model and MA model, now I have ARMA1. And what does the notation mean? The first number means the degree of the autocorrelation, autoregressive order. And the second number means the degree or the order of the moving average process. So remember that we talk about AR series and then we talk about MA series, but this is just the special case of all the stochastic process. And now we are going to generalize it by how? We generalize it by combining those two facts into one of the series. So this is the mathematical representation. So if I have a series looks like this, so on the left-hand side, xt minus psi minus, times xt minus 1. Okay, so tell me, what does this looks like? This looks like a little bit looks like what? This looks like the AR model, right? So if we go back to the very first question that we have in this problem set, if we move, can I use? If we move this term to the left-hand side, and we get rid of the drift term, yt, it's equal to like yt, something like this, right? So this is just the vanilla flavor of the AR1 model. So this is the same. So now we take a look at what the ARMA looks like. The MRMA looks like this. If xt is a series, it's a stochastic process, like this. Okay, so this is the AR flavor here. And on the right-hand side, looks like this. It's not only depends on epsilon t, but also depends on epsilon minus t. Okay, so now you're supposed to have a theta here. Maybe there's a typo. No, let's see. Maybe not. Okay, so this is the process of the AR and Ma1. Remember, left-hand side is the degree of the autoregressive model, and right-hand side is the degree of the moving average. Okay, so derive the first and the second moment of xt. Okay, so now we could calculate it by our hand, right? So let's take a look. Well, what does it look like? So if I have a series looks like this, xt minus. So again, this is the AR part, right? And this is the MA part. Looks like this, and uh, AR MA 1. This one usually we will specify as P, and this one we usually specify as Q. So P is the degree of AR, Q is the degree of the MA. So first moment and the second moment of the XT. Okay, so how do we do so? First of all, first moment is usually not hard to find, right? So let me see the first moment. Okay, so xt is equal to, right? All I do for the first step is to move the negatives cx minus t to the right hand side. Okay, and then the next step is to give a expectation operator for all right hand side variables. And luckily, once again, we found out what? We found out expectation of a parameter constant times a random variable means constant times expectation of a random variable. And a constant become a constant, right? What about this too? They both equal to 0 because it's a white noise, right? Okay, and now we need to apply for a stationary property. Okay, so ARMA is a stationary process. This you have to take it given information. So now ext is equal to E1 minus this ext become this. Okay, all right. Then it's the harder part. That's the second moment for this series. Well, it's not hard. It's just there's a little bit of the trick inside. So if you couldn't figure out by yourself, it's quite normal. But if you Google it online, there are a lot of resources tells you that uh, you could find it. Okay, so let's see. Um, and also in a textbook, you have some of the references. All right, so now let's see how can we find out the second moment and the autocorrelation function. Okay, the covariance of the xt, it's the variance of the xt, right? So let me see. So first of all, we need to find the same period of the covariance. So covariance xt is actually equal to variance xt. And sometimes we call it gamma 0, right? So it's like same periods outcome variance. Okay, and how do we find so? So covariance xt it's equal to right? So xt will be ext will be xt. So we don't need to worry about this first. Okay, so this will be something we already figured out. Okay. Okay, so gamma 0 is equal to expectation xt. So that means if I substitute xt, one of the xt, this looks like, right? So what do we do next to, so, okay. Well, let's see, should be, so gamma naught will equal to this. Plus epsilon plus epsilon t minus 1. Okay, and what's this? This will be gamma naught. It's equal to c gamma 1 plus, here is the sigma square plus sigma square 1 plus this. So those two terms you could calculate by yourself. Okay, but this is the first important question. Sorry, will be the first important condition. Sorry, I just lost my connection to this. Okay, and then the gamma 1 will be equal to let me go back again, and then so first of all, gamma 0 going to be ext, xt, and this one are going to be okay, and gamma 1 so xt. Just plug in, substitute and plug in. You will get this. Gamma 2 will be t minus 1 xt minus 2 plus t xt minus 2 plus t minus 1 t minus 2. Okay, so if we simplify those three equations, we will get gamma naught is equal to this. Gamma 1 is equal to this. Okay, so our goal is to find out gamma 0. Okay, our goal is to find out gamma 0 because this is a variance, right? But we also need to know gamma 1 because we want to find out what's the low one, what's the correlation function looks like. And now I have two equations and I have two unknowns. How do I figure it out? I plug in here. Gamma naught would equal to C gamma naught plus this plus this plus this. Gamma naught will be and just collect the terms. You will get gamma naught. It's equal to C squared gamma naught plus 2 sigma. So 2 sigma and 2 sigma C. So gamma naught for this ARMA process will look like in the end. Okay, and then what about gamma 1? So gamma 1 is just plugging this into this term, right? So gamma 1 will be C times and you will have gamma 1 is equal to 1 minus this psi 2 this 1 plus this. This is your gamma 1. Okay? So the answer key will be posted in the on the blackboard very soon. So let me just show you how do I simulate this in the R and find out the graph again. So basically, it's the similar idea. So if I share my screen here. Okay, so I need to share my screen. I need to share my screen. Share. Okay, so now, again, we just need to find a seed, right? So now if we need to define a seed first. So let's think that we are going to let uh, we are going to let um, C equal to phi equal to negative 0.6 and theta is equal to 0.5. Okay, so um, take a look of this. So what I'm trying to do is to simulate a R1 function, right? So simulate R1 function, I need to tell R what is this. I need to tell R what is phi and what is theta. Okay, so theta is here and C is here. Okay, and now I just need another seed. So let's see, maybe we try the seed it like this. Okay, run it. Then just using our ARIMA simulation function in R. Now, if I want to take a look at 10,000 observations, so you need to tell simulation function how many observations you would like, and this is the variables, the coefficient you want to specify. So AR coefficient is 0.6. So AR is phi, right? And MA is 0.5. So theta is equal to 0.5. So if you tell R will give you ARIMA function looks like this. Given the random seeds that you tell R, so this is the outcomes that you have. Okay, so if you want to plot it, okay, that's very easy as well. So you could type Psps Plot, right? Just run this sequence. So this is the outcome that you see. So as you can see, is this series ARMA1 is a stationary or not? So it looks like if we use our bare eyes to take a look, it looks like the expectation value of each period looks like around 0 somehow, right? That's because we don't choose a drift. There's no alpha naught in our model, right? So I only have the coefficient and between in the AR1 leg 1 period and MA 2 shock there. So I only have theta and alpha 1. I don't have alpha naught. Okay, so now it looks like it's a stationary mean is relatively uh, close to 0. Okay, and what about the ACF and the PCF looks like? So basically we just run this process. So ACF, autocorrelation function, as you could expect, this will looks like this. So because it has AR flavor here, so only have one spike, very oh, because it's MA flavor here, so you have very high spike first one. And then what about the PACF? PACF will look like this. Okay, and that pretty much is uh, the whole the structure of this problem set. So again, so by doing this problem set, what you are going to learn? You are going to learn the basic stationary time series model, autoregressive, and moving average, and their combination, autoregressive and moving average. So AR and MA and ARMA. Probably that's all I have right now. I will post the answer key, which is previous students' homework answer to this homework, and I will grade it pretty soon. Before I hope I could done it before Thursday. All right. So, uh, is there any question left.
Yeah, I was just wondering about for problem set 1. I know you had them graded last week, but I don't think it's visible to us, or at least
Okay,
not.
yeah, I will tell Jose. Let me let me just show you what I see here, because I already finished grading. Yeah, but Jose need to Professor Fernandez need to confirm it after, you know, after I grade. So
Okay, yeah, sure. As long as it
yeah, so
wasn't like
like
an issue where you
yeah,
thought
so
we all could see it but couldn't. Just wanted to clarify that.
okay, yeah. I will let him know. I will let him know. Promise, and copy to you. Hopefully today you learn a lot from today's review session. That's
Oh
all
yeah,
I. Yeah.
definitely. Yeah, thank you so much for doing
Yeah,
this.
no problem. Thank you for coming, Claire. Thank you so much. You are my only audience, and really appreciate your time. And do let me know if you still have any questions that you think um, it's a little bit hard, or like something I can't really explain very well. I know the covariance part, like to figure out the autocorrelation function, probably it's the hump here. But
Mhm.
the idea is quite similar, like we discussed last week. Like the only thing you need to know is the two formula of the stochastic process, right? Like a variance of the ax and plus by is equal to variance ax variance by plus 2 times their coefficient covariance. All you need is that, and there's just a small trick in the Ar2 model that you need to uh, if you use the decentralized covariance, that will be a lot more easier for you to calculate. But you don't have to do so. You can use the original formula for the covariance, like you minus the ext squared in the left hand side and the ext times ext minus 1 in the right hand side. That will give you the similar thing. Just go back to the calculation one more time, and then I think uh, you will understand the process. And the simulation and the code of the R, so far it's quite straightforward. All we need is using ARMA simulation function and ARMA simulation function in R, right? So that basically is it. That's it for today.
Thank you so much, and see you on Thursday or next week or
Yeah,
what.
yeah. I will let Jose know as soon as possible. Promise you. All right. Thank you so much.
All right, have a good rest of your day.
Bye bye.
Bye.